Hello and welcome back. Today we're looking at the Chapter 7 test review on exponential functions with financial applications as well. So the first thing we want to start with is for graphing, sketching an exponential function given in standard form. So what I would recommend that you do is always create a table and then substitute in some values for x. And I prefer for values for x, generally to start 0, 1, 2, 3, 4, maybe even a -1 in there. So in this one, because we're going to have growth, I'm going to make sure I'm heading more towards those positive x values. And so if I get to it, I'm going to start with, and this I might even want a calculator for. Let's try 1/4 times 2 to the 0. Well, 2 to the 0 was 1 times 1/4 is 1/4. And we might try making it 1. So 2 to the first is 2, and 1/4 of 2 is 1/2. And I could keep going and make that 2. 2 squared is 4, and 1/4 of 4 is 1. And so as I keep going, you can see I get the following table. Now these points, these pairs are actually points on the graph. So 0, 1/4, 1, 1/2, 2, 1, 3, 2, 4, 4. And so I'm going to plot those points, and then I'm going to connect them with an exponential curve. So next, let's take a look at a graph and be able to interpret some things. So first, we want to know what is the x-intercept. So it looks like we've got a horizontal asymptote here. As I go out to -7, I can see that this value isn't quite 10, but it's sure starting to get pretty flat and head in that direction. I don't think we're going to have a y value below 10, which means we will never actually hit the x-intercept. It just doesn't exist. For the y-intercept, I can see that clearly on the function. That's going to be the point 0, 60. So anytime I'm looking for a y-intercept, my x value always has to be 0. Sketch that horizontal asymptote. Well, it appears to be about there. And then we'd say, what is the domain of the function? So we're looking for all the possible values of x that we could put in. Or if we look at the graph here, well, how far can I go to the left? Well, I can go to the left forever. And we're getting steeper and steeper as we go, but we are still always moving to the right. So how far to the right can I go? Well, in theory, I can go forever to the right. So the domain is going to be all real numbers, or we could say from -infinity, as far left as left goes, until +infinity, all the way to the right. So for the range of the function, we want to look at our possible y values, and so the lowest this seems to go, again, we got to take a little bit of a guess here, but it does seem like it's going down to about 10. It's not actually going to reach 0 based on what we're seeing here. It's flattening out pretty quickly. All right, so that would be the lowest. The highest, we can see, it seems to be going up forever to the right, so we'd say +infinity. So if we look at the sketch of the graph, if we trace it left to right, we can see that we're going up as we go from left to right, so that is an increasing slope, and because we can see that it is not, in fact, a straight line, but a nice exponential curve, we can say that this is exponential growth. Now, if we look at the table, number 3, what we can see here is I go from 1/18 to 1/6 to 1/2. And it's hard to see with these, but we might start to pick up, well, there's 3/6 and 1/2, so I must have made that 3 times bigger. And that actually seems to be exactly what we do here. 3/2 is 3 times bigger than 1/2. 9/2 is 3 times bigger than 3/2. So we can see that we're multiplying by 3 every time. As soon as we see that we're multiplying by a certain amount, a constant amount every time, and we're not adding or subtracting, as soon as we know we're multiplying by a fixed amount, we know that we're looking at some kind of exponential. Now the question is the y value getting bigger as x gets bigger? Do we see something like this, where as I go further to the right, the graph keeps going up, and that is the case. So that's exponential growth. If I look at the next one, if I go from 2 to -1, and -1 to 4 to -7 to -10, well, I'm starting to see this pattern that I am decreasing. I'm subtracting 3 every time. So that's not exponential. If I'm changing by adding or subtracting a constant amount, that's going to be linear, and because x is getting smaller, y is getting lower and lower as x gets larger and larger, what we can see here is that y keeps getting lower and lower as I keep going further to the right. So that's a negative slope, so that's linear decay. Let's take a look at number 5. I've got a straight line, so this is going to be linear, and I trace left to right, and my finger goes up as I trace the graph going left to right, so that must be growth. So that's linear growth. If I look here and I trace, I can see first it's not straight, so it can't be a linear function. And as I go left to right, my finger's going down, so it can't be growth, it must be decay. We've got a curve with a negative slope. The value of a collector car can be, so let's look at number 7. The value of a collector car can be modeled by the equation A equals 89,600 times my base here. Here's my growth or decay factor, 1 plus 0.046 raised to the t. So I can see here that as soon as I see this plus, I know I've got growth. If I've got a subtraction, or if my base is less than 1, then I've got decay. So the rate percent change is going to be right here. Now we want to remember that we've got to write this as a percent. So we'd say that this is 0.046. If I move the decimal 2 values to the right, I get 4.6. We could also say, let's take 0.046 and multiply it by 100. If we do that, we get 4.6%. Now finally, they want to know what will be the value of the car in 10 years. Piece of cake. Grab your calculator and make t equal 10. So type everything in. Let's do that together. Let me pull up my handy-dandy calculator. So we're going to do 89,600 times 1 plus 0.046, close parentheses, and we are going to raise it to the 10th, because that's how many years we're looking at here. So if we do that, we get about 140,000, which is not quite what I had there. Sugar. Well, I'm going to go with the calculator one here. 140,483.35 Okay, let's take a look at 8 here. We've got our exponential function here. It models the population of a small town as a growth or decay. So I got to look at my base that the exponent is attached to, and I go, ooh, that is less than 1. That is decay. My initial value, here's my A value. Here's how many people are in the town to begin with. 2,169. The rate as a percent of change per time period. So here is where we're going to want to get a little bit careful. So remember that my base is always 1 plus or minus something. In this case, I end up with 0.96. So I know I've got to have 1 minus something to get a number smaller than 1. So I want to know what that something is. So I'm going to add r to both sides, and then I'm going to get r alone by subtracting 0.96 from both sides, and I get r equals 0.04. And if I change that into a percent by multiplying by 100, I come up with 4%. Okay, let's take a look at 9. So the value of Mary's house today is $189,000 and increases by 5% each year. Create an equation that models the value of Mary's house after X years. So we always want to remember that we should have an exponential function in the form of my initial value A times some growth or decay factor B, some people call it a multiplier, always raised to the X. So the first thing I'm going to do, well, what's the initial value of the house? What's my A value? Well, that's what the value of it today is, $189,000. It's increasing, so in my B value here, by 5%. I know the increase tells me I'm going to be adding, and the 5%, if I do 5 divided by 100, I get 0.05. So that is going to be my base, 1 plus 0.05, or 1 point, or you could add them and you could say it's just 1.05. And it's going to be raised for how long? For X years. We can figure it out later. We'll just call it X today. Maybe we'll want to know different numbers at different times, so we'll just leave it a good X. Let's take a look at 10. A patient has 9,000 white blood cells per microliter of blood. However, the number is decreasing by 7% each month. Very concerning. Write an equation to model the number of white blood cells in the patient at X months. So first thing, again, we go back to that general y equals a times b to the x. I want to know, well, how many white blood cells are they starting with? 9,000. So there's my a value. If we're decreasing, it's going to be 1 minus 7%, or we could say 0.93% or 93% remaining, or my base of 0.93 as well. So I'm going to say minus 7% as a decimal, 0.07. We're going to have this continue for X months, hopefully not too long. That would be concerning. If it goes on for too long. Okay, let's take a look here at the end. Write an equation to model the function graph to right. Well, we really need 2 parts. We're always looking for the same 2 parts. Y equals a times b to the x. And we want to know, well, what's a, my initial value? That's very easy to find on a graph generally. It's my y-intercept. So wherever x equals 0, there's going to be my initial value. So that one we can see is just 100. My b value is a little bit more difficult to come up with. So here's what we know. We know my a value is 100. And I know it's being multiplied by some b raised to the x. And I know this is where I start at 100, but if I go 1 x value to the right, I'm at 1 y equals 150. So, and that isn't x values over, that's just 1 x value over. So we can say 150 equals 100b. And we want to get b by itself. So a way that we can do that is to unmultiply b by 100. I'm going to cancel out that multiplication by 100 by dividing it by 100. But once I do that, I have to do that to the other side. And so I end up with b equals 1.5. So now that I've got that, I know my a value, I know my b value. I can plug them in there and raise it to the x. Now, we could do something similar over here, but it would be a little bit trickier. We start at 100. We end at 506.25. And now we have to think, well, how many x values did we move going from 0 to 4? Well, that'd be 4. So we'd have to divide by 100. Then we'd have b to the 4th equals something, and to undo that, we would have to take the 4th root to be able to solve that. All right, so hope that helps, and we'll see you in the next one.